Welcome. In this video I'm going to show you how you can perform a one-sample trinomial test using Python. I'm running Python 3.818 in JupyterLab. This test can be used as an alternative for a one-sample signed Wilcoxon signed rank test or a one-sample sign test. It's a test for a median. The difference with the sign test is that this does not exclude the scores that are tied with the hypothesized median. To load some example data, I'll first import pandas and then use their read CSV function to load in a file student statistics. This has a lot of data in it. Well, not so much, but I don't need all of it. I only need one ordinal field as an example, so I'm going to be storing as an ordinal field to teach motivate, which was how motivated the students felt if they felt motivated by the teacher. Using the value counts for this, we can see that, for example, 7 students said agree. You might notice these are not in order. Fully disagree, neutral, disagree, agree, fully agree. So it might be nice to have a separate coding, where as a dictionary, where I simply have the options in the proper order. I have a separate video where I show you how you can use my stickpad library that simply has a function that can do this in one way immediately. In this video I'll simply use Python only. So I'll first actually convert that pandas series to a list, then remove any missing values. So then we are having the ordinal field list cleaned. And then actually also replace everything with their numeric value by using the coding dictionary we assigned earlier. And now I should have all the numbers as all the data as numeric. So if I do print ord field num, it should give me only numbers. Set the hypothesized median, in this case a 3. We need to determine how many scores were above, below, and how many were tied with the hypothesized median. So I can simply use the length, and then for every score that is if the difference is above 0, if the difference is below 0, and if it's equal to 0. I'll add those as my counts, and the total sample size is of course the sum of all of these. Oh, I didn't execute this one, so now run this one, and that should give me the counts 13, 29, and 12. The assumed or the expected proportions that we need to also have for the multinomial distribution is for the tied scores, we're simply going to use the proportion as it was in the sample, and then for the positive and the negative we're going to assume 50-50, so everything that remains after this. So for the tied scores, it's simply the number of tied scores divided by, actually I can simply use n over here. Then for the positive, it's 1 minus the tied proportion and then divided by 2, and then set the same one for the negative differences. And that gives me the probabilities, or the expected probabilities. Then we have actually most of it what we actually need. We can now calculate the probability of having a result as in our sample. So what we do is we use the multinomial distribution that has this scary looking function. I actually have a whole separate video on the multinomial distribution itself. But with 3, the formula actually comes down to this. And as you might notice, there is just a factorial sign. Luckily we can import that from Python's default math library, and then we can just fill out. We have all these values, and this is just the probability of positive raised to the power of the number of positive. So we can simply enter everything. It looks a little bit long, but it's simply filling out the formula. This is just the probability for this specific distribution. However, we want to know or more. And we can't use the cumulative distribution function because that's for any different sample sizes, but we want to have a difference of what we have in the sample, or even more extreme. So what we need to do is we need to sum over all the different, all the possible trinomial probabilities that we have, starting from our difference that we have in the sample, all the way up to the maximum possible difference, which is just the sample size, and then calculate all the trinomial probabilities for each of those combinations. We'll then simply use the those for our number of positives and negatives, and then the number of ties is actually everything else that remains. Alright, so this looks scary, but what we're going to do is we're going to sum over from the number of differences, or actually the difference that we have, so the number of positives minus the number of negatives, and then the absolute value of those. That's the ND, and we need to sum all the way up to n, so that's being arranged over here. And then from J0 to, and this is the floor function, so just round down, or actually just make it an integer, which we should also round down, so that's being done over here. Then we set as our number of positives, we set simply that j, so that's the first one. Then we add the index, the I, so here's the j plus I, that's covered over here. And then the last one for the number of 0 differences, we're simply going to use this one. And then we just fill out that formula just as we did over here, but then with the new values for the end pos, the end neg, and the end tide. And we keep on summing this up, and in the end multiply that with 2. And that should give us then eventually the same result as you would get if you use my own library and the function specified for this one sample trinomial test. This value is below the usual 0.05 threshold, so we would reject the null hypothesis and then state that there is a significant difference with the hypothesized median. Alright, I hope that this video was helpful, and thank you for watching.